Hello everyone, welcome to the webinar, and we're going to get started soon and just have more people join in and download the software. We would start in 3 minutes. Thank you. Okay, I think we have enough people. Again, first of all, thank you all for joining into today's webinar. Today's webinar, we're going to be focusing on the Zenmuse L1 solution and in terms of research in accuracy. The reason we're hosting this webinar is to help, first of all, address some of your common questions about the L1 system and some common questions you may have in the L1 solution, and such as the 100 seconds IMU calibration if that's needed, and etc. The goal for the webinar today is after today's webinar, you'll be able to help have a better understanding of the system and its capability, and in terms of the solution, what you can get from the solution. And for today's webinar, we have invited Christian Stalling from BAAM. And Christian is a very experienced photogrammetrist, and he's also a heavy L1 user, and he used the L1 system with TerraSolid and to generate many successful outputs and projects. Hi, Christian. You mind do a quick introduction and just to give everyone a little bit about your background and what you do in BAAM?
Thank you, Ron. Hello, as Ron said, my name is Christian Stallings. I'm a certified photogrammetrist. I've been working in the remote sensing industry for about 15 years. My first experience was with the beginning of the digital aerial mapping age with the first digital mapping camera by ZI. And I've had the opportunity through that time to see the technology change and play a role in looking at and understanding those technologies and finding the limits of those technologies.
Thank you, Christian. Thank you, Christian, for being here with us today. And just a little quick introduction from my side. Hi, everyone. My name is Ron Lee from DJI Enterprise, and I work for the Solutions Engineering Division. My role in DJI Enterprise is to help conduct a better solution for vertical users, and specifically focusing on mapping and surveying industry. So my role involves a lot of research in LiDAR as well as photogrammetry sensors and software and hardware to help improve the workflow for people using these sensors with our aerial platforms and improve the efficiency overall. So today we are going to cover a few topics with you all. The first one is the solution and workflow overview. So we will be covering the L1 solution as well as its workflow. We will provide you an overview and a bigger picture of how that works. Just in case some of you may not have much of experience with L1 and just want to learn more about the sensor itself. And I will also be providing some solution highlights as well as improvements we have been done for the past year, just to show you guys what exactly you're getting out of the solution and what are some benefits you're getting from the L1 system. And Christian, from professional perspective, would provide some studies regarding to the L1 accuracy, because after all, that's what most people really care, is the accuracy of the system. And with that being said, I can get started. Just to give everyone who doesn't know the L1 system a quick background. So DJI L1 or Zenmuse L1 in full name is DJI's first integrated airborne LiDAR payload. We call it payload because it's attached to our UAV platform. Well, in this scenario, DJI Matrice M300 RTK. It is a payload. It is a fusion payload that integrates the LiDAR sensor, which is manufactured by Lightbox. Also, a RGB camera with mechanical shutter can also be used for photogrammetry missions if needed. And when we're talking about the L1 solutions or the workflow, it's extremely straightforward because all the components end-to-end is DJI solutions. So first step is the hardware preparation. We have the UAV platform, which is being the Matrice M300 RTK drone, and we have the payload, which attached on the bottom of the drone, which is L1. That's the hardware setup. No additional components or hardware is needed. Or software, or additional software is needed. And we have mission planning software, which is being the DJI Pilot 2 app. Now, this mobile application is built into the M300 RTK remote controller. So if you're using the M300, you have that software building automatically. So no additional software needed or hardware needed. And consider the Pilot 2 app is a data collector. So it helps plan out a mission, but also helps you collect that data. So the Pilot 2 has the functionality and to generate missions for L1s. And we have the L1 profile, sensor profile, built into the Pilot 2 app. So user will simply need to select L1 as the output sensor, and the Pilot 2 would generate the mission autonomously, and it would fly the drone autonomously to collect that data. Once you have the data collected, then is the data process part. So we have our software called DJI Terra software to compile and convert the raw LiDAR data collected from the L1 system and generate the deliverable output, which is in LAS or other formatted point cloud data for further use and further classification. For example, TerraSolid, which Christian is going to cover in his slides to describe that methodology. But when we're looking at the workflow in general, and when we overview the workflow, you will notice that it's very easy in terms of in terms of executing and creating and getting the data. Easy as 1, 2, 3, right? So we have mission planning, and that is the question for where, what, and how. Where are you going to plan the mission, and what exactly are you trying to scan, and how you're gonna scan it. So the mission planning part is exactly our software. The Pilot 2 app is essentially the solution designed for mission planning. So where you want to fly the mission, you just need to define the boundary within the Pilot 2 app, and what are you scanning specifically. And DJI Pilot 2 app is going to generate a flight route based on the boundary you selected. How are you going to fly the mission based on what scanning pattern, based on what sampling rate, and what's the speed, how you're gonna do it, and that can be all configured within the application. Raw data collection, that's the only step you need to do when you're on site. So when you're on site, the time is valuable. You don't want to waste so much of time being on site and do the mission planning or even the data process. So we separated this portion of workflow out from the mission planning. So you do the mission planning offsite. So you do the mission planning in the office and create the mission and make sure your mission is saved. And then you can have someone or pilot to be on the field and collect all these data. The benefit for doing that is that eliminates the user error, because when you're executing out the mission for data collection, the pilot actually doesn't do any flying. The drone flies itself because the mission is pre-planned. So that eliminates the user may have error, causing the data output is inaccurate. And the last part is the data process stage, which would take more time. But Christian, from your experience, would you say that the mission planning as well as the data processing is significantly more important compared to the data collection?
Say that again, Ron.
Yeah, the mission planning as well as the data process stages are significantly more important compared to the raw data collection.
The data collection has to be correct, and exactly. I can say that one of the challenges that many people have when it comes to LiDAR systems, and we'll talk about some of the benefits of the Zenmuse L1 in this regard, is that if the data is not collected correctly, it's difficult to do anything afterwards. And through the DJI Pilot, some of those things that people can do incorrectly are corrected for. So for example, getting your heading alignment correct is very important for initializing your IMU or your inertial navigation system. And DJI has a bunch of fail-safes built in that allow you to do that automatically, which is very helpful. A lot of times when it comes to mission planning with other systems, it's very important that you consider how long your flight lines are. DJI automatically takes care of that for you, which simplifies that process. It takes some of those variables out so that you have more successful missions.
Yeah, thank you, Christian. And exactly. So if you don't collect the data correctly, the result is not going to be good anyway. So, and you cannot change anything. But like Christian mentioned, we have multiple functionalities building to our mobile applications that is fail-proof. And here are some benefits and highlights for the system. First of all, the system is extremely ready to work and easy to use. As I mentioned, no additional hardware setup, or no GPS or GNSS receiver needs to be mounted on top. No additional batteries needs to be mounted for the system or for the LiDAR module to function. And the entire system is RTK and PPK system ready. And the sensor itself, the L1 sensor itself, is getting powered from the drone directly. So if your drone has a power, the sensor has a power, and it transmits the data via our Skyport mount. So it communicates with the drone and pull the telemetry data from the drone directly from the drone and read those data and write those data into the images and LiDAR information. So because of the high integration, we'll be able to control the entire weight of the L1 system less than 1 kilogram, and that outputs 40 minutes of operation flight time per charge. So per flight, you'll be able to have around 40 minutes of operation time. That is very important because you don't want to waste too much of time setting the unit up when you're on the field. Again, saving a lot of time on the field is important to boost up that efficiency doing the operation. And in addition, we have Pilot 2 app with all types of mission planning building directly to the remote controller, and that is completely free for user to use. And we have autonomous LiDAR IMU calibration. Now, we've been hearing a lot of people asking us whether you need to do IMU calibration for the L1 LiDAR. And just like Christian mentioned, we do have a fail-safe proof mechanism within the Pilot app. It's when you're executing out a mission, the drone does the IMU calibration in flight, before flight, and after flight autonomously. So you don't have to pause the mission every 100 seconds and do the IMU calibration anymore. And we have a free software, which is called DJI Terra software, to compile that data and output that data. And that software is free for user to download and for user to use. So when we have a look at the workflow on the right side, again, the first three stages, hardware preparation, mission planning, mission execution, and data process, that's all being done with DJI. Afterwards, we have a output, which is the point cloud data, and that can be used for third-party application and further applications. So that was the workflow for the L1, very general. But let's talk about some improvements and updates we have been done in this year, actually. How are we consistently improving the system by pushing out software updates as well as firmware updates, which indicates we are continuously supporting this platform and this product and improving the system efficiency and ease to use by releasing these updates. So first of all, autonomous LiDAR IMU calibration now is available in all custom mission types. So within the Pilot app, whether you're doing a waypoint mission or if you're doing an ortho scan or an oblique mission or a linear flight, doesn't matter what mission type you're using, you are now able to have the Pilot app pre-planned the IMU calibration route directly within the Pilot app. And we have now just released a feature called Smooth Point Cloud feature within our Pilot 2, within our Terra software. That functionality would reduce the thickness of the point cloud layer by over 50%. As you can see on the right side, we have a chart just to show you that comparison. That black dots indicates the point cloud layer before having this function enabled, and we have orange point cloud data indicates having that feature enabled. That reduced the point cloud layer and point cloud thickness by 50%. That is now available in the Terra software. We also have a new Terra. We also have a functionality in Terra software building. It's called a strip alignment. So the strip alignment would make sure each flight strips, each data collected from each strips is aligned when within the cross-section region. So we also have check shots import and accuracy test functionality building to the Terra software. That means you can import your check shots, define the coordinate system of the check shots, and output an accuracy test report. And that's going to indicate your accuracy. And that's building directly into the Terra software. PPK process building, so no third-party software needed to process out the PPK data for Terra to process. All you need is toss in a RightNext file, which is a time frame which contains your flight time, and you just need to toss that file, RightNext file, into your raw data folder and have their Terra process. So no additional software needed. And now you have another options to adjust the point cloud density based on the sampling distance. So that creates a more even point cloud density across the entire scan. As you may know that the point cloud density might be higher in the region where different strips aligned. So this functionality can reduce the point cloud size dramatically, and based on your need, you can adjust that. So we also have elevation offset. So once you have your average altitude difference from the check shots accuracy test report, you'll be able to apply that average altitude difference offset into Terra again, just to better improve the accuracy of your results. And as I mentioned, we're continuously improving this product by releasing more and more functionalities. With that being said, I am going to pass my microphone to Christian, and Christian is going to cover more in terms of the accuracy of L1, how or what accuracy level can the L1 produce, and what methodology he would be using to justify that. All right, Christian, I would pass the mic to you, and I will make you the presenter now.
Okay.
Before Christian starts his section, I do want to let everyone know, if you have any questions, please feel free to utilize that questions box under the webinar panel and ask any questions you may have, and I will help address some of the questions, and we will do a quick Q&A session at the end of this webinar. All right, it's yours, Christian.
Ron, can you see my screen?
Yep, I can see your screen.
Perfect. All right. Well, thank you very much, and thank you everyone that's on the line. First, a little more about BAAM Tech. So BAAM Tech is part of our portfolio. It's focused on procuring the right equipment to our customers and providing. We provide detailed training so that they can be successful with those tools, including the DJI products. You know, we like to say that we like to meet our customers where they are in their journey. If they're a small survey company, or if they're just learning to implement LiDAR, or if they are a larger company that they need to have custom built software or algorithms. So we have a professional services group that really works with customers to help them identify the tools that make sense for their workflows, and we help them on their journey as they learn to use these things and become successful with them. Our geospatial data science team is led by actually a world-renowned data scientist and developer, Aaron Smith. That part of our business is really focused on helping our customers solve unique problems that there isn't a current solution for. So we help build custom algorithms and software for the next generation of geospatial problems like carbon capture, precision ag, sustainable forestry, things of that nature. So, like I mentioned, we like to meet our customers where they are. We have a real crawl, walk, run approach with this. A lot of our customers are working in the geospatial field, but maybe are less familiar with a lot of the remote sensing technologies. So we work closely with them to understand where they are on their journey and to help them identify the right tools to approach the problems that they're working on. We work with them to provide them very detailed workflows, not just hardware. Oftentimes I think people see customers purchasing hardware as the end of the transaction, but we really see it as the beginning of our journey with our customers. And we spend a lot of time to make sure that they're successful with those tools and that they're making money with those solutions. So that's BAAM Tech. So as part of that, every tool that we sell, we want to understand intimately and understand the use cases for those and the capabilities that each of those tools have. And of course, one of those is the L1. So we're going to kind of go through a few things about LiDAR so that we can understand how to assess the quality of a system like the L1. So we're going to first go through some LiDAR basics. For a lot of folks, this might be pretty common stuff, but I think it's really important that we understand these basic components of a aerial LiDAR system so that we can also understand the sources of error in those individual components. And the next we'll go through how we actually test the accuracy of a LiDAR system and how we break down those individual components to test those things. We'll talk about the accuracy and performance of the L1 over time. You can always look at a snapshot of a system and that may not tell you necessarily the quality of that system. You could have a very bad project, you have a very good project, but what's really telling is how that system performs over time. And then we'll really dive into some individual projects to really assess some of the intrasystem relative accuracy aspects of the L1. I think that's the most intriguing part of these systems and probably the thing that I hear the most about. So we'll spend a great deal of time kind of talking about the precision of some of these components, mostly the laser itself. And then finally, we'll just kind of summarize those tests and conclusions for the system. So the L1, to me, is a very fascinating piece of hardware. I've been, as Ron mentioned at the beginning, working in this industry for about 15 years. When I started, I worked with the ZI digital mapping camera and the Optech Gemini system. These are systems that were over $1 million. They're not things that were easily accessible. When I was in college, you didn't have access to these types of tools. And what's been amazing, and it has always drawn me into the drone part of this industry, is that all of a sudden there's accessibility to these tools to a lot larger group of people using them and younger people who are interested in our profession. And that really democratizes. It allows newer, diverse people to come into this market and utilize these tools in ways that weren't affordable, they weren't feasible in the past. And the Zenmuse L1 is a tool that I saw as, another potential tool to do that, to further democratize these things in the same way that we really do with photogrammetry over the last 5 years. But with that said, if the tool does not create the quality data that is required, then it's not going to achieve those goals. So it's really important for us to understand the quality of the information coming out to that, and you can't look at just price alone. So we want to thoroughly understand, what is the quality of this? What's the actual achievable accuracy that you can get from the L1? And how consistently can you do that? If it's randomly not working well or performing well, that's not a reliable tool. And then we wanted to kind of understand the inter and intra-project analysis of the L1. As I mentioned, really understanding within the data itself, and then over many projects, what that looks like. And we'll kind of go through the absolute accuracy of the system, as well as some of the relative accuracy things that we look at in LiDAR systems, if that's within the swath itself. The swath is the individual flight line. Each time you fly down a line and you turn around and you fly back, we call that a swath. And then how well each of those passes or swaths match to each other. So section 1, we're going to kind of talk about some of the components of a LiDAR system and what we use LiDAR systems for. And this is going to be a little simplified, but in the interest of time, we're going to really just focus on these 3 basic components, which is the laser head itself, the ranging and detection part of the system, the positioning system that tells us where in space we are, and the orientation system. So first, starting with the LiDAR head, the ranging and detecting system. LiDAR is an acronym, stands for light detecting and ranging, and it's similar to sonar or radar in the sense that we send out a pulse of energy. We measure the time that that pulse of energy takes to hit an object and then come back. And then because there's some constants that we can know, like the speed of light, we can measure how long it took to hit that object and come back, multiply that times the speed of light, and then we can divide that in half because we're only interested in the journey there, not necessarily the journey back. And we can determine how far away the object is from us doing this, which is great, but in order to do that successfully or have anything meaningful, we need to know where in space we are. Before we had systems that moved around, what we call kinematic systems, we had static systems, and we still use static systems all the time. But we can know fairly accurately where we are in space with a static system, and we can get a scan, and we can put multiple scans together from known locations. But that becomes challenging when you're on a moving vehicle, like an airplane or a drone. We need a way of positioning ourselves in the world. And to do that, we use a technology that everyone has in their pocket every day, GNSS, a form of GNSS that everyone's familiar with is GPS, which is the American constellation of satellites. And it's just a means of sending timing and information from satellites to a receiver to get an accurate location of that in space. Now, there's different things that we can do with that. We can do that in real time to get more accurate location. If with a known location or a base station, we call that real-time kinematic. We can also do it post-processed after the fact with the same information. But in both cases, we're using a reference station. We talk about having a base and a rover to create corrections for that. The DJI system M300, I will say, is what we call full GNSS. It's using multiple constellations. It's using the American system GPS. It's using the Chinese system Beidou. It's using the Russian system GLONASS. And it's using a European system Compass. So all those systems together give us a full GNSS system, and there are different wavelengths on those systems. Getting into too much detail, but it allows us to get a much higher accuracy than, say, the GPS or GNSS system on your smartphone. So we have position, we have ranging and detecting, so we're able to know where we are and how long it takes us to shoot a laser from the system to hit an object and come back. But the last part that we need to understand is our orientation and bearing of the system, right? We need to know which direction we're pointing the system to truly put it in real world space. So to do that, the last major component of a kinematic LiDAR system is the IMU, or the inertial measurement unit. And this allows us to have orientation. The L1 has a built-in IMU, and it also has a secondary sensor that allows us to get additional corrections. It has an optical flow system on it that you can see circled in red right there. And that helps us overcome some of the challenges with some of these IMU systems that we use in these types of electronics. This type of IMUs we call a MEMS IMU, which is a more modern technology. It's these days it's less expensive, but the accuracies are actually improving quite a bit compared to older technology. We traditionally used what's called a FOG IMU, which had mechanical gyroscopes in it. They're more expensive to manufacture than the MEMS IMUs. But using these systems, the optical flow and the IMU, we're able to pretty precisely understand our orientation in space. And we put all three of these things together. We have our ranging and detecting, we've got our position, we've got our orientation. We're able to create a rich point cloud of a location in space and put together a 3D representation of that, like this example of a substation right here. And then from that, we can measure and extract different information from that. So some of the different use cases that we use LiDAR for, we use it for topographical mapping quite a bit. Some other examples, you may use it for floodplain studies, individual tree analysis. With these higher density systems, it's kind of interesting the things that we're able to do now in different types of forestry applications. And another very common application, you can see this example right here, is power line mapping, where we can understand the real world conditions of those power lines very accurately in real time. This is something that photogrammetry sometimes has challenges with, especially with thinner wires, the ability to identify those in 3D space, because we need to triangulate those versus a LiDAR system where we're using a active sensor and we're able to identify those power lines more confidently than with a photogrammetric approach. So now we know the basic components of a LiDAR system. It's important to understand the sources of error associated with those individual components. So as we stack these different things together, all these components are going to compound in our total error budget. So there is some inherent inaccuracy or lack of precision in the laser system itself, and we need to account for that. Same goes for the GPS or GNSS system, the IMU, even our ground control, our system we use to validate, and even the coordinate system that we're using to project that in as a representation of the real world, because the world is not a flat piece of paper, but all of our coordinate systems, by and large, our planimetric coordinate systems are a flat 2D space with a 3D or with an elevation. So all those things can compound together and create sources of error in our products. So what are some of the errors or lack of precision that you can find in the DJI L1? So first, we're going to start with the scanner that we talked about. As Run mentioned, the scanner in the L1 is the Livox Avia scanner. And based on their own spec sheet, it has a precision of 0.78 inches at 65 feet. This is not exact. These specs are not published, but just given on a linear scale, if we extrapolate that out to 400 feet, that's a potential inaccuracy of 5 inches almost. So just with this one component, you can see that the potential to stack these inaccuracies together can increase quite a bit. Next, we have the GNSS system itself. This is our positioning system. Vertical is typically less accurate than horizontal with the GNSS system. At the highest, the best you're going to get is 0.75 inches, and that's really pushing it. Depending on things that can happen, float, bad satellite constellations, solar activity, there's things that can affect the quality, and it can get much worse. But when people talk about getting accuracies higher than this without control, it's very difficult to believe, because there's just some inherent limitations to the GNSS system itself and the inaccuracies associated with that. Finally, the IMU and the optical flow system inaccuracies. So the IMU that's used in the L1 has a stated accuracy of 0.03 degrees in the roll and pitch and 0.08 in the yaw direction or the heading. That's common for a lot of these systems where the heading is going to be less accurate than the roll and pitch. That's actually always really been the case. And something that a lot of these systems suffer from is what we call heading drift. And that's why it's really important to do corrections to fix your heading often through your flights. If you've used some of these systems, they'll either have you shorten the length of your lines so that your heading doesn't drift, or in the case of the L1, it has some built-in features that allow the optical flow system to create compensations for that, where it stops, it lunges backwards and then lunges forward again within the middle of your flight to help maintain your heading. So if we look at all these inaccuracies and we put them together, you can see that they can compound to be a pretty large number. That's not to say that you should expect these accuracies, but this is the potential inaccuracy built into a system like this. And if you're just looking at a spec sheet for this, you can it's understandable how you could reach the conclusion that you can't do quality mapping or create accurate products from a system like this. Thankfully, we have ways of measuring that. So we have different specifications to do that, to measure the quality of these systems, the absolute accuracy, the relative accuracies. And we've had mapping standards for quite some time. We're going to focus on the United States. Those are the standards I know. And we've had mapping standards since at least 1941. ASPS actually helped the US Bureau of Budget for those national mapping standards. You'll sometimes hear people say NEMAS, which is the acronym for National Map Accuracy Standards. And then the other one that you might hear people talk about is the NSSDA accuracy standards, which are the ones from 1989, excuse me. And then of course there's the USGS LiDAR base specification, which is less about accuracy. There's parts about accuracy, but it also references the ASPRS specification we're going to talk about a lot, and it's more about the quality of the products that we create. And that's still an active specification we use for making certain products for the USGS. But the spec that we're going to talk about is the one that is currently used. It is the gold standard, and it's proven itself to be hold up well over the time since it came out first in 2014. And it was built out of a necessity to update the standards, to be more agnostic to the technology, because as we know, this technology moves quick, and we needed a robust accuracy standard that allowed us to adapt to the changing technology, but still hold it accountable. So I really encourage everyone to look at this specification. We're going to look at just one part of it, and it's really the vertical accuracy part. So we're going to look at this graph quite a bit today, and this is actually a consolidation of several different charts. This is section B7 through B9. I put it all together for ease of use for what we're going to talk about today. And some people may not like this, but I actually converted most of this into feet as well. All the data we're going to look at is in feet. So if the numbers look different, that's because they have been converted into feet. But you'll see that this is really broken down into, two major sections really. When we first talk about table B7, which is the portion about absolute accuracy and relative accuracy. Those are the main things that we're going to be focusing on. There's also the contour interval comparison. When we talk about NEMAS, 1 foot contours, or ASPRS class 1 contours, these are legacy standards, but they're still pretty common. Things that people talk about when they're communicating the required accuracy for a project. So in order to talk about our desired outcomes for this, it's important that we first create some nomenclature to work with. This is not common nomenclature, but we needed some way of talking about the desired outcomes for the projects that we're going after. So the first one, we're going to talk a lot about standard grade. Again, this is not a real quote grade. This is just a way for us to easily talk about it in the context of this research. But I will say this quote standard grade that we're talking about is very, very common. So suitable for 1 foot contours data is by and large the majority of the mapping that I've experienced in my 15 careers here in the United States. So the section that's highlighted in red is probably the majority of every project that I've been involved with in the United States. It's very common to meet that accuracy standard. So the next one we're going to talk about is this quote max grade. And again, these are arbitrary terms, but they're important in the context of this conversation. You'll hear people talk about design grade and survey grade, which I think are terrible names and they're misleading. That, you know, there's no hard definition of what is a design grade or a survey grade. And the reality is there's very few remote sensing products that were required to meet this quote max grade, design grade, survey grade, whatever you want to call it. But when it comes to conventional survey, oftentimes the accuracy requirements for those products shot to shot will be somewhere in the range of 5/100ths of a foot or 6/100ths of a foot, somewhere between these two tranches that are in this table right here. All right, so ASPRS breaks these accuracy requirements in these two major sections in table B7, which we talk about absolute accuracy and relative accuracy. And it's important to understand these when we go and look at this information. So when we're talking about absolute accuracy, we're really talking about, you know, how close it is to a known value coordinate. How easily can someone else go and use a different tool, a different get a measurement on a different day, different way, and come up with the same information as you. That's the absolute accuracy of it in the real world. But when we're talking about the precision of these equipment, we need to talk about the relative accuracy, which is really the repeatability of the measurement. And oftentimes we see this bullseye example here showing kind of precision and accuracy, but it's also, I think it's helpful to think of it as relative accuracy and absolute accuracy. At the bottom, you can see this is a cross section of some flight lines. Then you can see both their misalignment vertically from the yellow line and the purple and blue line, but also the thickness of the LiDAR itself, which is a function of its relative accuracy, not necessarily how well it measures compared to your ground control. So first we're going to talk about absolute accuracy and the system over time. As I mentioned, you can have projects that come out really well or really poorly, but what really matters is the consistency of that system over time. How well can you continuously get the same results? So through our work with customers over the last year and change with the L1 system, we've completed 31 different projects that had digitally leveled control. So all that had a vertical accuracy of roughly 1/100th of a foot. And all the projects that you see here were classified using the TerraSolid L1 wizard. We'll be talking about that a lot. They have some classification routines that are tailored for the L1 system. But you can see two different representations of those accuracies over time. The one on the left, the vertical error spread of all points, is a consolidation of all those projects. And you can see it has a somewhat Gaussian shape to that. The large majority of those points are hitting quite well. If we look at the table on the right, you can see a breakdown of each of those individual projects with the digitally leveled control. And we look at that first column where we have the red box, you can see the minimum root mean square error, the highest accuracy projects we've had, the max, which is the worst, and then the kind of average of all those projects. So the absolute best was 1/100th of a foot, which is absolutely incredible. The max difference is a little over 2/10, 0.23 feet, which is still quite good. But the average project, we've seen this play out time and time again, is that we typically, with this ground classification macro, using TerraSolid, we see consistently around 600, 700ths of a foot with the L1 system and absolute accuracy. So again, going back to our table, we're looking at absolute accuracy for non-vegetated areas. You can see that we are consistently, for all those projects, getting an absolute accuracy greater than the requirement for that quote standard grade mapping that we defined. And oftentimes we're getting better than this quote max grade. So not only are we achieving the accuracies we want to produce the products that our customers want, but we're doing it consistently, which is very important for these types of systems. So that is the L1 over time. Next, we're really going to dive into a project that we did with George Butler and Associates for Kansas Transit Authority back in December of 21. And this will show some of the relative accuracy of the L1 system. So as I mentioned, in December 21, we worked with George Butler and Associates on a project for the Kansas Transit Authority. They're doing a bridge replacement. And as part of that project, they were mapping the area leading up to the bridge on both sides for about a half a mile each side. And they wanted to understand the accuracy and quality of the L1 system in comparison to the conventional approaches they were going to use for that project anyway, as well as some mobile LiDAR, aerial mapping, and photogrammetric approaches using the P1 system by DJI, their camera. So in order to do that study, it was important that we had very accurate control, and we had a lot of it. So magnails were placed. We had 30 control points, validation points throughout this project. I shouldn't call them control points. They're actually validation points for the entire project. And all of those were digitally leveled. Next, for the survey process, for the conventional survey, they did something that's definitely unique, but it's quite interesting. Is so GPS was used for the topographical survey, but for each shot that was taken, they spray painted a point on the ground, and that way we were able to go back and check those. And then all those shots were digitally leveled as well. So it was a very accurate survey that we were able to use for comparison for the L1. I don't know what just happened. Sorry, apologize about that. There we go. Sorry. So for that, we did 3 different flights. Run didn't mention it, but for the L1, there are a couple different scan pattern options in the LiveVox Avia. So we really wanted to understand the effects of those scan patterns as well as altitude on the system. As I mentioned, the further away you get from your object, the less precise your laser is, the less precise your orientation information is going to be. So one of the assumptions is that the closer we get to target, the higher accuracy we can potentially yield from that project. The scan patterns that the LiveVox Avia has is what DJI calls repetitive and non-repetitive. And a repetitive pattern is similar to a traditional LiDAR pattern where it goes left and right of nadir, back and forth. But the non-repetitive mechanically moves the entire LiDAR system as well, and it creates a pedal pattern where it's still going left and right, but the entire thing's rotating, so you get this gyroscope effect. And so that can allow you to potentially get greater look angles and penetration of vegetation, but it also means that you're going to revisit the same spot multiple times, which is, with the lower precision of the system, potentially just propagates your precision errors and makes them worse. So we wanted to see the effects of those compared to Flight 1. So we ran all that data through TerraSolid L1 macro and did the ground verification on those. This is still absolute accuracy assessment. And we had a root mean square error for those somewhere around, the first flight was 200ths of a foot. Our second flight, root mean square error was actually the highest. We actually had one outlier point we'll talk about later. And the root mean square error on that was around 600ths of a foot. And the final flight, which surprised me on the repetitive scan, still had a root mean square error of about 300ths of a foot. So as I mentioned, there's a very rigorous ground control process for the conventional survey and to digitally level all that information as well. So because we had that information, we had the opportunity to see a much higher sampling than just 30 shots compared to the ground. So we actually had almost 300 shots from that survey, or excuse me, 176 shots, forgive me, from that survey that we were able to compare. And the results I thought were staggering. So the worst shot that we had in all of that missed by 0.263 feet. But the root mean square error on all these different flights was 300ths of a foot up to almost 400ths of a foot, which again, incredible absolute accuracies. So if we were looking at that alone, from an absolute accuracy standpoint, we're well enough above the requirement for standard grade on a lot of shots, which is 176 is definitely statistically significant. And oftentimes we are better than requirements for a max grade topo. But absolute accuracy is only one part of the thing that we look at. So we obviously needed to understand the relative fit. And this is the thing that I think is really unique in LiDAR right now, that I love having this conversation, because how the automotive grade lasers are changing the way we think about LiDAR. So, if we go in and measure a profile view of our LiDAR, we can see that there are a large degree of inaccuracy. So, how can we have an absolute accuracy that's so high if our relative accuracy is really low? How are we able to get these types of results? To me, it really comes down to effective LiDAR processing. Getting your data, and I don't care if it's the L1 or another system, getting it out of your processing software is only one part of it. There's an entire post-processing process. And depending on how you do that process, you can manipulate data to make it look very poorly. I've seen people take L1 data and ran poor LiDAR macros on it, and they can make it look very bad, which some of it I think has been very dishonest. But if it's processed properly, you can get really incredible results. And as you've seen, you can get very consistent results. As mentioned several times, we recommend the TerraSolid software suite to process this. They have some tools. There's an L1 wizard that really simplifies this process for the ground classification, as well as classification of other features for the L1 to optimize it for the data extraction. They're one of the most trusted names in LiDAR software. They've been around forever. And actually, they have a webinar tomorrow. If anyone's interested in learning more, they're going to be talking about some new tools they built with TerraMatch for the L1 system that fits with everything that Run and I are talking about. It's just another tool to help better your information. So, excuse me. So now we need to test the relative accuracy of the system. So to do that, we took all the same information and we broke it into 6 different data sets, 2 different groups. So group 1 was those 3 flights with all the points that we talked about, and then group 2 was the ground classified points using TerraSolid. And one of the ways that we test relative accuracy is a planar fit model. So what we do is we find flat areas and we fit a plane to that flat area. And once that plane is fit to the flat area, we're able to see how much the points protrude above or below that plane. Fortunately for us, this data set had a pretty flat road leading up to the bridge on both sides that we could use to do this type of analysis. So we were able to create a whole bunch of different planes, 52 in total, for the road section in areas that it's pretty flat. It's obviously not perfectly flat, but it's as flat as you're going to probably find in the real world for this type of in situ measurement. So this is an example of one of those individual planes that you can see. And what we're visualizing here is how large the difference is from that plane above and below it. So if it's dark, it's above it. If it's white, it's below it. And on the left, you can see the full unclassified points. On the right, you can see the ground classified points using TerraSolid. And all of a sudden, some of the patterns of the road actually start to emerge from that visualization right there, where you can see the ruts in the road a little bit. You can actually see the fall off on the edge where the plane goes slightly over, where the road starts to drop off on the asphalt. Another way to visualize this is with a histogram, and this is, I think, a more meaningful way to look at this. So this is an example of that same plane. On the left, you can see the distribution of that error on each side of the plane. The red dotted line represents where the plane is. The blue represents where the different buckets fit either side of that plane. And then the red curved line is the Gaussian fitting of that histogram. So on the left, you can see the spread is quite high. We go all the way up to plus or minus 0.2 of a foot on all those points. But when we look at the ground classified, you can see that goes down to 0.04 of a foot plus or minus on each side, somewhere in that realm, 0.05 of a foot. So we consolidate all those together for those 3 flights, we can see some interesting patterns emerge where, again, all those points for all those planes consolidated together, the Gaussian fit is not great. There's a couple reasons for that. I mean, one is just the inherent precision of these types of lasers, as well as there is some bias from vehicles here and there that make those lean a little bit to the left. But at the bottom, you can see they're very consistently in that 0.75, 0.05 range on the max. And if we go and look at the relative accuracy requirements for that, you can see that we are oftentimes in here. I will say this is based on max difference, and there are different ways of doing this particular test. We did it on every single point that were either in the raw point cloud or in the classified point cloud. What I think is interesting though is if at 95% of those points on the ground classified, so flight 1 was 95% of the points were 0.018 feet or lower. Flight 2 is 0.023 feet or lower. And flight 3 is 0.024 feet or lower. They're very, very, that distribution is very low, which is quite incredible. There are outliers that go higher than that, but 95% of them fit underneath that. So this is going to be controversial, but in my mind, that meets the spec for standard grade, and but not quite for max grade. And I think this is where there's an opportunity for us to revisit this part of the ASPRS specification, because if the point is to look at the precision of the laser head itself, there's actually a lot of these quote automotive grade lasers that don't meet this requirement at all. But if we can use intelligent algorithms to create a derivative, the actual product we're going to work with, and get these kind of accuracies, does that count? Does that meet the specification? And it's not entirely clear if which way it is. So I think this is something that as we have the opportunity to introduce new LiDAR systems, we need to look at this and account for it. All right, so the last thing we're going to look at is our swath to swath fit. So our within swath that we just looked at, that's looking at the precision of the laser head itself. Our swath to swath fit is looking at how well our inertial navigation system works, which is the combination of our GPS, our IMU, or optical flow system. So as we fly the same place over and over again, how well do each of those passes match each other? And in this picture right here, we can see a profile where this has been exaggerated, where data set's been pulled apart, where we see a center barrier for the road, and you can see kind of 2 different places where it's at. They've been shifted from each other. So the red is a different flight line from the green one below. And so this is an example of where something does not have a good swath to swath fit. So there's different ways that we can measure this. One way that's pretty common, although it's more of a quantitative approach, is to do a swath or a delta Z raster. So this is a great way to visualize large sets of data and looking at how well those swath to swath fit. So these are a rasterized product showing the intensity value from the LiDAR as well as the delta between those individual flight lines on top of each other. And then you can see the color gradient on the left-hand side for that. And these were done at a sampling of 1 foot pixels. And flight 1 and 3 actually had a really good fit from each other. We saw earlier the absolute accuracy where we had some shots in flight 2 that were off a little bit. We actually had a little slightly higher absolute accuracy than we expected. And that's because of some slight misfitting that happened on the south side of flight 2 that allowed a couple of those points to be higher than we expected, but still well within the realm of what's required for standard grade mapping. So kind of the conclusion of this, that, you know, the L1 system, it's not perfect, but when it comes to the ability to meet and produce the mapping products based on the ASPR specification, we have found, and we've worked with our customers quite a bit on this, that you can be very successful with this. You can absolutely meet those accuracy requirements. I think there's a lot of disingenuous, overblown misinformation about the quality of these systems. Is it capable of doing everything? Absolutely not. But for the value and what you're able to achieve, I think it is a very significant piece of technology that has a huge place in a lot of workflows, especially for these smaller survey firms who it may be difficult to justify buying a $150,000 piece of equipment and then an airframe to put it on with little experience doing it. This is an opportunity for smaller firms to make very, you know, quality topographical maps with a much smaller investment. And we feel that they can do that consistently and get very accurate results, provided they're utilizing proper workflows, that they're trained how to use these things properly. And then the last thing, as we talked about in the within swath relative accuracy, I think there's an opportunity we need to revisit that part of the accuracy standard when we talk about laser precision, and maybe find a way to quantify both the precision of the laser itself, but also the precision of the derived point cloud from that we're going to use in our final products. One thing that wasn't mentioned in here, there was one last part about point density. It just didn't really necessitate a slide. We flew all these projects at over 400 points per square meter. The algorithm that we use in TerraSolid actually thins what becomes our ground classified points down to, you can set that value. We typically set it to 0.3 feet, which still gives us a point density greater than 20 points per square meter, which is the requirement for the highest, the max grade precision. And then finally, we still have some future testing to do. I think there's some interesting ways we can have a qualitative approach to the swath analysis that we're looking at, similar to the planar fitting we did with the within swath analysis. As Run mentioned, there's some new algorithms in DJI Terra. None of those were tested here. All this was prior to that release. So we are very interested to see how that new algorithm affects or improves the quality of a project like this. Initial results look really good. I'm pretty excited about it. And then finalize our comparison with some of these other technologies from the mobile LiDAR system. And then when it comes to precision, there's this vertical edge accuracy on curbs and other man-made features like that that have quick, small vertical separations that I think warrant some additional work. And then last but not least, I really encourage everyone to go look up some of the different geospatial data standards that we use, especially the ASPRS positional accuracy standards. I think anyone who is making products with any of these systems needs to know this standard well and utilize it. It's a great way for us all to communicate the quality of the products that we're making. And with that, if there's any questions, I think we've left a little bit of time to answer any questions.
Thank you so much, Christian. And we did receive tons of questions. Mostly are related to the product and solutions in terms of the software. But we do have some questions for you, Christian. Let's see. He was asking, do you have an example of how thick a forest canopy can be and still be able to reach the ground and map bare ground, or percentage of the vegetation cover versus number of points that reach to the ground under the vegetation?
That's a great question. All right, this is something that's as old as LiDAR. So, everyone always early on said LiDAR can see through trees. LiDAR does not see through trees. It is an active sensor, meaning we create our own energy, and we're measuring, how that energy hits a object and comes back. The higher the density we have, it's still a shotgun approach. So the higher the density we have, the greater opportunity we have to see in between those features. So a better rule of thumb is, if you imagine you're an ant and you're in a forest at noon, and if you can see specks of light on the ground, there's an opportunity for that LiDAR system to penetrate and identify those locations too. Now, this is where the repetitive and the non-repetitive come in. So if with the non-repetitive approach, you have the opportunity to get different angles into the forestry. So with our customers, oftentimes we tell them, if you are doing hard surfaces, roads, we typically recommend to use the repetitive scan. If you're trying to get better canopy penetration, we recommend the non-repetitive, but that does increase the potential noise in your scan itself. But you also have to compare that to what would be the conventional approach, which oftentimes we're cutting 100-foot cross sections or 50-foot cross sections through there. So how accurate is that of a representation of how the topography changes over that 100 feet? So there's not a hard rule. I'll say we've worked with folks in July in swampy forests in central Florida and still got incredible penetration down there to bare earth on there. But it's not any LiDAR. It's not a perfect tool. But the greater the point density you have, the better chance you're going to have to see that. And then of course the more look angles you have, the better chance you have of seeing that. Some of the challenges really are not with those heavily forested areas. Sometimes it's more with when we have shorter vegetation actually.
Right. Thank you for that. And I noticed people tend to ask more questions about which flight setting works the best and which flight setting would apply to my scenario specifically. I do recommend you guys to go to our L1 product page, and under download section, we actually have a document. It's named L1 Operation Guidebook. And within that document, you would find some recommended settings for the sensor when you're doing mission. And we have settings, for example, scanning pattern, for example, gimbal angles, for example, velocity and speed. You can use those information as a template almost. It doesn't work, of course, for all the scenarios. I bet, Christian, you have the same experience. There's no one profile or one setting that works for all. And I just saw someone that was asking about, let me see. Many documents recommended 50% overlaps for the flight mission. Is it still best general settings, or also would the slower speed works better than the faster speed when you're doing scanning? Based on your experience, Christian, would you say that really based on the scenario and based on what exactly you're scanning?
Sure. So first, when it comes to traditional manned or piloted LiDAR systems, we conventionally flew about 30% overlap. And we would use that overlap, not necessarily to get our point densities or get features, but it's reference to the other flight lines. We talk about the swath to swath so that we can calibrate or boresight that data. Our recommendations to our customers are to have at least 30% overlap, up to 50%. It really depends on the site, but through the data processing, we don't recommend to necessarily use that overlap information in your final products. We often cut it. So I wouldn't recommend using it to get your densities ever, but you want to have enough so that when DJI Terra is doing its strip alignment, or if you're using some other workflows like Terra Match, that you have enough reference information to accurately keep that data together.
Definitely. Let me see. We do have more questions. I think this one's for you. Is there any effect on accuracy between single, double, or triple return modes?
Potentially. It depends. So some things that we didn't go over, we didn't go through. There's a part of the ASPR specification for NVA and VVA, which is the non-vegetated and the vegetated analysis part of it. So if you flew first return only in a vegetated area, your chances of getting any kind of canopy penetration are very, very low. If you're doing only hard surfaces, it's probably not going to matter at all. I haven't done a thorough enough analysis to tell you that effects of the different return patterns over a non-vegetated area, for example. But with LiDAR, there's always some kind of trade-off, right? There's no free lunch oftentimes. So if you get multiple returns, let's say you want more returns, and this applies to a lot of LiDAR systems, but also the L1. If you want 3 returns, our repetition rate, how fast we can shoot that LiDAR, actually decreases because there's only so much the computer can do at once. So a lot of times we will slow the aircraft down to shoot 3 returns, or if we've got kind of a mixed use site, we might recommend shooting 2 returns at a faster speed, so we're more efficient. So it's always a give and take. There's not a lot of operational scenarios that we recommend single return. In fact, I would argue that if you have a scenario where you only need a single return, there's probably a photogrammetric solution that will work just as well.
Yeah, usually I do dual returns for all the scans because you never know. You probably have area that you don't even notice that has vegetation covered, even within the urban region. So usually I do dual. Next question is, when doing LiDAR surveys and the ground elevation differs greatly, would follow terrain be the best option to fly, or fly at a consistent height?
Terrain following for us. You know, if we talk traditional piloted systems, we're so far away that our overlap's going to be affected if we fly continuous height. But it's not really going to affect the data so long as we have enough overlap. Oftentimes we're dealing with terrain changes, especially out west, where they're greater than the altitude of the system. And so not only if you stay at constant height, are you going to have to increase your overlap to make sure you maintain enough overlap for your calibration, but you're going to just complicate your mission. The one thing that's really nice about the L1 is it's pretty straightforward, and we provide our customers the workflow to easily get elevation models into there to do terrain following. And with the terrain following and the block missions, the wide area missions, it will still automatically do the calibration, which is really nice. So you have the best of both worlds. We really like that workflow for areas with lots of terrain. So I would recommend using elevation models.
Yeah, so just in case you guys don't know, we have multiple ways to do terrain follow mission within our software, and the digital elevation model, you can import whether it's a digital elevation model or digital surface model using a digital elevation model file or digital surface model file, and import that into the remote controller, and the remote controller would create a mission, just like Christian mentioned, automatically for user to fly the mission. And IMU calibration is there again autonomously down. We also have a new method, which is the Aster version 3 digital elevation model online available. So if you want to use the Aster you can now download that directly into the Pilot app app software. So that's free also, and that's available. And that's actually a new feature we just released about a month ago. So in case you guys don't know. Okay, thank you for that. And next question we have, let's see. Let me see. How deep can the L1 sensor sense in terms of swallow water depth? So L1 is not a bathymetric sensor, so it doesn't do underwater.
Well, yeah, just I guess maybe to add to that. So there are different time of flight LiDAR systems, and we use different parts of the electromagnetic spectrum. All of the systems we use for topographical mapping are near infrared. In fact, the L1, I think it's 908 nanometers. And when we talk about automotive grade lasers, if it's a Velodyne, if it's a Hesai, all those are going to be roughly around 906, 908, somewhere in that realm. If we're talking about systems that are built specifically for topographical mapping, they're closer to 1500, 1550, like a Regal system, for example, or an Optech system. Those are going to be a little higher. And those diodes are more expensive to make than the ones we use in the automotive. Now, if we're using a bathymetric system, which has better water penetration, that is going to be the green light. And so these systems aren't built to necessarily penetrate water in the same way that a purpose-built bathymetric system is.
And here's another question. How does fog or rain affect the data collected with L1?
It's gonna, like any LiDAR, it's going to affect it. It's fog, depending on the amount of fog. We're shooting on a pulse of light. It's going to hit things. It's going to bounce back. So if there's things in the atmosphere between the laser and the target, it has the potential to affect it. So you could fly on a rainy day and you could see that rain. You can fly and have birds go underneath you, and you're going to see the birds potentially in your data sets, especially these higher point densities. So all those things are going to affect your data.
And does the flight speed affect IMU drift or swift? Is it better to fly faster or slower? So yeah, go ahead, Christian. I might have additional points for this.
No, you go ahead first.
Okay, so we actually, if you're doing this manually, we do recommend you to fly between 5 meters per second to 10 meters per second, with the speed being consistent as possible. But however, when you're doing a mission, we actually would limit your maximum speed when doing a mission. So you wouldn't go higher than certain speed based on your elevation, or excuse me, based on your flight height. So that way it's like a fail-safe, I guess. But based on your experience, Christian, would you say you prefer any preference on that?
I mean, like I said earlier, everything with LiDAR that you get, you have to give something up. So if you increase your speed, your point density is probably going to go down. So depending on what you're doing, we have a flight profile we really like that's repetitive. It's around 200 feet, it's around roughly 8 meters per second. We get around 400 points per square meter. And we, for our customers, they have a lot of success with that flight profile.
Yeah, that's another great point. It's about point density. When you fly slower, you have significantly more amount of points, and in the software, you actually would be able to see the estimated points per unit area, and you can use that as a reference. All right, let me see. will the gimbal angle affect the accuracy in any way?
Yeah, it can. So there's another part of LiDAR we didn't really talk about, which is beam divergence. So imagine you had a flashlight and you're right up against a wall. That circle on the wall is pretty small, but as you back away from that wall, it gets wider and wider. Lasers are the same way. So then imagine you have an extreme angle on that beam, and that can create greater horizontal ambiguity. So if you gimbaled it at a very extreme angle, your horizontal ambiguity is going to increase for the system. Now we typically, what I think is interesting about the L1 though, it's the only fully gimbal mounted integrated system that I'm aware of, and it allows us to do some kind of unique things. So that gimbal can be an advantage for certain things. An example would be doing electric utility collects, where we can pitch that angle just ever so slightly, 5 degrees or so, and it allows us to get better hits on the fronts of the towers. But you can theoretically do some really interesting collects that would be impossible with other LiDAR systems, where we can point the thing straight out, like the picture you see right there, and maybe map the side of a cliff. So there are some unique advantages to that, but it can create disadvantages if you're creating extreme angles that for the beam divergence.
Yeah, that is exactly correct. Because of the scanning pattern and the field of view in vertical, usually we recommend people to tilt the gimbal slightly just for the power line collections, data collections, like Christian mentioned. And you can also find that in the operation guidebook, as I mentioned earlier. But yeah. Joe was asking, could you take photos at the same time while doing the LiDAR mission?
Yes. So there's a couple different options there. And actually, this is something that's kind of cool. As Ron mentioned, it's a mechanical shutter. It's similar to, it's the same sensor as what was in the Phantom 4. And we help customers with electric utility projects, for example, where we need an ortho, but they also need the LiDAR to do the electric utility work. And you don't have to do the same overlap that you have to do for a photogrammetric mapping mission. You just need enough overlap to bundle the images or tie them together, and you can actually use the elevation information from the LiDAR system to ortho rectify the imagery. This is similar to how we've always done manned orthos before drones, where we didn't have these ridiculous overlaps. We had 60% forward overlap and 30% side overlap, and we would use other elevation model sources, either photogrammetrically compiled or from USGS, to ortho rectify it. You can do a very similar process with the L1, where we use the topographical elevation information from the L1 to rectify the imagery from the camera system on the L1. So you can get both without having to have a flight profile where we have tremendous overlap. So it's very efficient.
Exactly. Yeah, exactly. And this year we actually updated the pilot app and within the pilot app mission planning, are you able to see, because the field of view for the LiDAR sensor is different compared to the camera field of view. So you actually be able to adjust the overlaps ratio for the LiDAR sensor in the LiDAR mission. And when you change that, you will be able to see estimated overlap ratio for the visual sensor. So that way, you theoretically can boost up the overlap ratio and be able to collect 2 sets of data. One's the LiDAR and one is photogrammetry. And that photogrammetry set of data not only can be used for colorization, like colorize the point cloud, you can also use that, as Christian mentioned, for also mosaic process as well with sufficient overlaps. I think we hit our time, and we still have a lot of questions. But if you have more questions regarding to the sensor or any questions overall, please feel free to reach out to us by reply to your webinar invitation email, or you can email to me directly. It's going to be run.li@dji.com. Thank you very much, Christian, for attending. We have learned a lot of information from you today and appreciate it.
Thank you very much for having me.
All right. All right. Hope everyone have a great day and see you.